to Data Science with Python. In this video, we're going to look at assessing the residuals for constant variance and make a residual plot. All right, so we're going to pick up where we left off last time with this fitted model, CT1_res. If you haven't gotten this far, you might want to go back and watch the previous videos. These are all linked together, and it'll save us a whole bunch of time. All right, so the very first thing we probably want to do is create a residual plot. And this is pretty easy to do. What we're going to do is use our PLT functions for our matplotlib.polyplot. And we're just going to simply put in here PLT, if I can type it, figure, open parentheses, close parentheses, so it creates a new picture. And then I'm going to put on here CT1 diameter, that's my X, right? And the second thing I'm going to plot on here is CT1 res.resid. And those are the residuals. And the symbol I'm going to give it is O, which is a little O. And then I'm going to PLT show the figure. So sometimes this you might need to have this if it shows up on yours to get it to actually show up. All right, so let's run all of this and see what happens. And sure enough, we get a plot here. And what we're looking for is constant variance, which means the spread across here is similar everywhere. And if you look, it's kind of not. It seems to be clumped here, and then it gets wider as we go along. So that seems to be the general setup. But what we'd like to do is actually test this with what's called a Brecht-Pagan test. So we need to set up the data for that first. So we want to conduct a Brecht-Pagan test. Hopefully I spelled that right. And we'll talk about what that is in a minute. But first thing we're going to need to do is we're going to need to get two quantities. So we're going to need the residuals that we have squared. So I'm going to get those from here. I'm just going to copy and paste. And there's several ways you can get a square, but the easiest way is just multiply it by itself. That'll do it, sure enough, and it should work. Now, we're going to have to actually modify this and turn this into an array using NP or NumPy. Okay, so this is going to put it into an array that the regression later will like. The second thing we're going to have to do is we're going to have to get a data set that we're going to regress this against that has each of the items squared. Okay, so I'm going to use NP, not each of the items, just the X value squared. So NP column stack is the function I'm going to use, and it's going to put these next to each other. And you can look at them on your own. They're pretty easy to do. I'm just pulling off the diameters here, and then I need an X squared, which is diam times X dot diam. Okay, and this should give us what we want. So we need residuals squared, and then we need a data set with X and X squared in this. Once we have this set up, we just run a test on this, and I'm going to actually run the model, but we'll hide it so you won't see it until we do the hypothesis test. So run the regression for this test, and it's basically exactly what we have up here. We're just going to swap things out real quick. It's exactly the same. Our Y now is resid2, and our X is X2. And we're going to call this something else. We should probably call it, like resid2 res. Or you could call it the BP test, whatever you want to call it. So now we can conduct our hypothesis test. So our hypothesis is H naught. The residuals have constant variance across all of the X values. So it doesn't matter where you're at, the variance is the same. Versus the residuals do not, if I can spell, I cannot spell today at all, do not have constant variance. And this would be called heteroskedasticity, if you want a big word to say. So we need a significance level. Remember, this is something we don't want to reject, so we should be a little bit careful with it. So alpha equals 0.0002. Okay. We need a decision rule. Actually, we need a test statistic. And we are going to use the BP test. Okay, we'll just leave it at that because we've already ran it. Let's see here. The decision rule is always the same. If the p-value is less than alpha, we reject H naught. All right, now we can actually run this thing. So execute. For us, it's going to be really easy because we just do resid our model to res, and then we can do summary and get the summary out and look at the F test. Right, we want to see if any of them are significant, and in this case, the p-value associated with this is, well, let's run this. Let's see what we get here. And let me scroll the picture down here. And you'll see up in here, you'll see there's an F statistic right here. And you'll see the p-value associated with that F statistic. So this is, if you had picked 0.05 for this sucker, you'd be rejecting it. And you'd be hating yourself. Because now you have to do some sort of weighted least squares on it. But here we chose a significance level small enough that it's not really going to affect anything. All right, so we can make a decision. Our decision is since the p-value, if I can type it, equals that number is greater than our 0.002, which is equal to alpha, we fail to reject H naught. Okay, and our conclusion, we have insufficient evidence to claim that the regression residuals do not have constant variance. Does that mean they do? No, doesn't mean they do. It just means we can't detect it, and even though in this case there is quite a bit of evidence for it. But let's not worry about that right now. We're going to start going on to ANOVA next. We'll come back to multiple linear regression later, but we'll start ANOVA in the next video, and I'll see you there.